Hello and welcome to this lecture. In this lecture, we will finally after a long time study the logarithm function. Okay, so you might have studied logarithms earlier in your school and all that, but to introduce the logarithm function, it turns out integration is a very nice tool to use. Okay, so a lot of a very good way to introduce logarithm function is through integration. A lot of people introduce it as inverse of the exponential and then study the properties. We will also see that. You will see that the logarithm function ends up being the inverse of the exponential and all the powerful properties that logarithm has, we will prove all of that here. Okay, so once you do this, we have a new function log x that you can play with. Okay, so we introduced the exponential function when we studied power series and all that, and then we saw a lot of properties of the exponential function, and we are using it in limits and integration, differentiation all over the place. Likewise, we will use logarithm also and study all of that. But first, let us see how the log function is defined. Okay. So, for that we need to go back to this fundamental theorem of calculus. We had one fundamental theorem of calculus, which was it was like a definite integral a to b f of u du is the antiderivative of f of b minus f of a, right. So, that is one thing. So, you can slightly modify that kind of theorem to get this very nice theorem. Okay. So, I will just walk you through this, and then I will tell you why this theorem is so interesting and important. Okay. So, supposing you start with f, which is an integrable function on an interval a b. So, what is integrable? You remember any bounded function is integrable. Okay. So, it is quite a, well, when I say any, of course, there are some pathologically badly defined functions which will not be integrable, Riemann integrable, but we will take typical useful practical f. So, f will be integrable on a b. Let us say any bounded function which is good and bounded and practical, that function. Okay. So, you fix one point x in that interval a b. Okay. So, you have a function f which is everywhere in a b, and then I pick one point x in this a b, and now I am going to define a new function capital F of x. Okay. I define this function as the area under the curve of f of u from a to x. Is that okay? So, this is f is integrable. So, this thing is very well defined. So, this function is also very well defined. So, this is a very interesting idea. Now, I am using the integration operator to define a new function. Okay. So far we have not done that. We always thought of integration as area under the curve, but now I can make one of the limits of integration as a variable, and now I have a function, right. So, when I change x in this interval a b from a to b, this f of x will also change, right. So, this value also changes, and I have defined it as an integral. Okay. Because I am defining it through the integration operation, I will get a new function here. In many cases it will be new, some cases if f is a simple function, then maybe you already know f, there is no need to do it. But in case, like for instance, a very ready-made case is when f of u, you do not know a closed form integral form, right. In that case, you can define this function, and anyway you can numerically evaluate this integral, right. I showed you some numerical integration. So, you can evaluate this integral and you will get the answer. It is area under the curve, you can approximate it in some way, you will get the answer, right. So, once you get that answer, you will get a function f of x. So, that is the way to think about this. Okay. So, it is much like the way in which we define power series, right. So, you do power series, you get a new function from the power series, no, that is how we got e power x and all that. Now, you can also use integration to define new functions. Okay. So, that is the wonderful idea behind this. So, what am I doing here? Once again, I have an integrable function on an interval a b, I take a point inside that interval, and then for every such point I can define a new function f evaluated at that point as the area under the curve from a to x of this f of u d. It's as simple as that. Okay. Now, this function has some really powerful properties. What are the powerful properties? The first property is that f is continuous on a b. This is, I mean, we won't prove this, but you can sort of see where this comes from. Okay. So, it is not too difficult to prove, because f is bounded, you will get all these nice properties. Okay. And then if this f, small f, happens to be continuous at one point x naught in the interval, okay, here is the huge property which I think is very significant. The derivative of capital F at x naught is going to be equal to small f at x naught. Okay. So, capital F is like an antiderivative of f. Okay. And this is not very surprising, right. I have been always trying to convince you that when you take a derivative, you go from you go in one direction, the opposite of the derivative, antiderivative, comes from area under the curve, right. Derivative is like the slope of the function, and area under the curve is like the opposite of that slope, right. How that function varies, in this area like the integration opposite, okay, integration and differentiation opposite, and this fundamental theorem of calculus part 2 sort of affirms that difference. Okay. There are various ways to quickly see it. Okay. One quick way to see it is, suppose capital F is the antiderivative of small f, right. So, then you will see here that this integral is actually some f of x. So you can imagine why this. So it's, I mean, maybe I should repeat myself. So this result sort of tells you that capital F will be like the antiderivative of f. Okay. So that's what this means at the end of the day. Okay. So you have a function f of u for which you don't know the antiderivative. Okay. How do you define the antiderivative? You simply define this integral, you get the antiderivative. That's what it means. Okay. So it's a very interesting way of doing that, and there are lots of reasons around it. But what I am going to quickly show you is a proof for the second part very quickly. It's a slightly technical proof. I will only give you the proof idea. So basically, if you have a function like this, and if you look at the derivative limit, right. So what is the derivative at x naught? It's capital F of x naught plus h minus f of x naught divided by h, limit as x tends to 0, h tends to 0, right. So this is my definition of derivative. Interestingly, this will become 1 by h. So 1 by h is as it is. F of x naught plus h minus f of x naught is integral from x naught to x naught plus h f of u du. Okay, because this guy, this first guy is integral from a to x naught plus h. This guy is integral from a to x naught. So if you subtract the two, you will be left only with the integral from x naught to x naught plus h. Okay, this is one of the properties of integration. Now, since f is continuous at x naught, there is this really powerful property, right. How do you think of continuity of a function? When you come close to x naught, you will be very close to f of x naught. You remember, that was the intuition behind the continuity of f at x naught, right. So that's all you have to use here, right. If I come with a u, if I come inside this interval and my h is tending to 0, then my f of u will also come close to f of x naught with some delta, and that delta will also tend to 0. Okay, so that's what this continuity means. You come close to x naught, you will be close to f of x naught, right. So that's the idea. So once you see that, this will tend to f of x naught. So this will sort of become f of x naught times h and h will cancel, you will get f of x naught as h tends to 0. Okay, so this is a proof idea. It can be made more rigorous, but this is the central idea behind how the derivative comes. Okay, you can also use some fundamental theorem of calculus part 1 and then do this. Okay, so this will also work out in that fashion. Okay, so I hope this is clear. I mean, the main idea is not the proof is not so important, but this idea is very important, that when you define a function like this, this capital F becomes like an antiderivative for f, small f. Okay, so that's a wonderful idea. Okay, how are we going to put it to use? Okay, so we can use it to define some special functions with desirable properties. Okay, so that's a utility, and let me start off that utility with defining the logarithm function. The logarithm function is a function whose derivative is 1 by x. Okay, so if you remember, we had derivatives for all, I mean antiderivatives for all x power a except for a equals minus 1, right. When a was minus 1, this 1 by x, we didn't have an antiderivative. Okay, that antiderivative we'll define as log of x. Okay, so there's one more choice here. Notice this. So from the fundamental theorem of calculus, it's very clear that I'll have to have an integral from some a to x 1 by t dt. Okay, or 1 by u du, whatever you like, and my x is going to be positive. Okay, why is x positive? I mean, that's a constraint that we're going to take. 1 by x for x negative is sort of, it's a flipped version, so we'll restrict to x positive. We'll see why that is important also. Okay, so you'll get integral 1 to x 1 by t dt. Okay, so this has the property that if you do a derivative of this log prime of x, I'm going to get 1 by x, right. So that I know from my fundamental theorem of calculus. But I have also chosen a to be 1. Okay, now that is actually an arbitrary choice. I could have chosen a to be something else, but choosing a equals 1 gives me one particular function, and you will see why that is very important. Okay, so soon enough you will see this one. It's not very important. I shouldn't have said it's important, but what I mean is why that is a choice. You can make any other choice here also. It doesn't change things, but traditionally, historically, people have chosen 1. And that's what we are doing for the standard logarithm, natural logarithm. This is called the natural logarithm, and for that you choose things like this. Okay, so that's the idea. So this is my log x function. It's integral from 1 to x 1 by t dt. Okay, so I've just plotted here this f of t equals 1 by t versus t. Okay, so this function will look like this. Remember, at 5 it will be 1 by 5. At 1 it will be 1. Right? Notice this thing. At t equals 1, you will get f of t is 1. At 2 it will be 1 by 2. At half it will be 2. At 1 by 3 it will be 3. So it has one sort of weird symmetry around the x equals y, you know, it has that very nice behavior, and it goes to 0 on this side and it goes to infinity as t tends to 0. Okay. So, you see why I am restricting x to be greater than 0, right. So, when I say, so my f of t equals 1 by t is continuous and nice for t positive. Okay. If I go across 0, I get into trouble, right, because then I have one infinite limit and it will get ugly, it becomes unbounded. Okay. So, it is good to do this restriction. Okay. So, now let us see some properties of this. I mean, it's important to see this definition and understand its properties. You will see this function log x has tremendously useful properties. Okay. So, the first property is log of 1 equals 0. Okay. Easy enough, right. So, it is area under the curve. So, see, remember this is 1. Okay, I have my 1 here, and then x could be anywhere on this axis. So, if I am 1 here and x is somewhere here, I will have area under this curve, right. If x is negative, I will have area under, I mean not x is negative, x is less than 1, x is 0.5 or something, I will have area under the curve here, right. So, you can imagine the area under the curves as x varies from 0 positive onwards, okay. But in particular at 1, I have no area, no, it is just 1. So, log of 1 will become 0, okay. Log of x for x greater than 1 is positive, okay. Why? Because I have integral from 1 to x, I have this area, so it is positive, okay. Now, for x between 0 and 1, log x will become negative. Why is that? See, if x is lesser than 1, I have integral from 1 to something lesser than 1, right, 0.5 or something, right. So, that for that what is my convention? I make it minus integral 0.5 to 1 by t dt. So, my log x will naturally become negative, okay. So, it is just the properties of integration, nothing else is going on, right. So, think about this, if x is greater than 1, integral from 1 to x will be positive, right, clearly that is the area. But if x goes lesser than 1, my integral still is defined as 1 to x, not x to 1, right. So, what happens because of that is, I have to integrate from 1 to x, which is minus integral from x to 1, and that makes log x negative for 0 to 1, x 0 to 1. Okay. So, very easy formula, I am not writing down detailed proofs, what I said can be written down, you can try that. Okay. Of course, by the fundamental theorem of calculus, log x prime is 1 by x for any x greater than 0, right. For 1 by t is continuous for any t greater than 0, right. That is why we are not including t equals 0, you know, I mean it is not continuous there. So, it is continuous everywhere. So, for everywhere where t is greater than 0. So, by just the fundamental theorem of calculus, the derivative of log is 1 by x. Okay. So, this is a huge property for us. So far, we did not have a derivative, now we have a derivative for 1 by x. Okay. It is a new function, we have learnt it for the first time, maybe you knew it before, but log x works like that. Okay. So, now notice this derivative 1 by x is also positive, right. At any x greater than 0, 1 by x is positive. So, that means log x is monotonically increasing. Okay. So, that is nice. See, log x is we know it is continuous, of course, from the fundamental theorem of calculus, and the derivative is 1 by x, again we know from the fundamental theorem of calculus. Because this 1 by x is positive, derivative is positive, so log x is monotonically increasing. Okay. So, at 1 it goes to 0, as x increases log x is monotonically increasing, as x decreases below 1 also it is monotonically increasing, but what it does we will see soon enough. Okay. So, these are quick simple properties for log you can figure out. Okay. But the most okay. So, let us, before we go on, I just want to spend some time on this integral and the area under the curve, and particularly study what happens as x becomes very large. Okay. So, we know log x is increasing, at log 1 is 0, okay. Log 1 is 0 and then log x is increasing after that, right, the area under the curve. What happens when x becomes really large? Okay. I am going to quickly go through this argument, I will not talk in great detail. The basic point is, as x tends to infinity, log x also tends to infinity. Okay. That is the basic point, final result will be that. I am going to quickly show how that works. Okay. So, log x integral 1 to x 1 by t dt, area under 1 by t from 1 to x, right. So, how do I get an easy lower bound on this? Okay. I mean 1 by t is a crazy function, it just keeps on changing. I go from integral from 1 to x here. Okay. So, that is my area. How do I get a bound on this area? Okay. How do I get a lower bound on this area? Once again we will use a Riemann-like trick. Okay. I will look at this rectangle of height half. Why half? Because this 2 is at half here, right. At x equals 2, this function is 1 by 2. So, I am going to look at this rectangle, that is half. Now, my entire area log x is greater than this half, right. You see that? Because this area is smaller than that. Then I will repeat the same thing, go to the next interval 2 to 3 and look at height 1 by 3. Okay. Once again I get half plus 1 by 3 is smaller than the entire log x function. And then I will go to 1 by 4, 1 by 5, so on till where I can go? I can go till floor of x, right? X is somewhere here. What is floor of x? The integer that is to the left of x, isn't it? The immediate integer to the left of x is floor x. Okay, so I will go 1, 2, 3 all the way till floor x, and I will forever be doing 1 by 4, 1 by 5, so on till 1 by x. Okay, so my log x is greater than or equal to half plus 1 by 3 plus so on till 1 by floor of x. Okay, we know this sequence, don't we? This is our wonderful harmonic series, and what happens as x tends to infinity to this log x will tend to infinity. Okay, so it's lower bounded by some area which is blowing up to infinity. Okay, so this is a quick proof using the definition of log x that as x tends to infinity, log x will become infinite. It will grow unbounded. Okay, so I mean keep adding all these properties, right? So log x, log 1 is 0, log x is increasing as x goes beyond 1, right? And it goes off all the way to infinity. It doesn't stop anywhere. Okay, very important property. So likewise, you also have x tending to 0 plus. If x is tending to 0 plus, again it turns out log x will tend to minus infinity. Okay, so that's the big result. Okay, the important to understand the big result, log x as x tends to 0 plus will go to minus infinity. Why am I saying 0 plus? I'm not allowed to go negative, right? So x has to be only on the, it should tend to 0 but only from the right side. Okay, that's what is allowed. Okay, here I have taken a particular x which is lesser than 1. Okay, and I am also showing on the curve x will correspond to f1 by x, right? See, f of t is 1 by t. So if I have x here, f of x will be 1 by x. Okay, so that's my line here. And what is this area? Integral from x to 1. Oh, I think there's a mistake here. Okay, so I am doing minus log x here just to show you that this minus log x becomes integral from x to 1, isn't it? So usually log x will be integral from 1 to x, but I am going to study minus log x, which is integral from x to 1. So that this minus log x will be positive. Okay, I can deal with it very easily. So area under 1 by t from x to 1. So this area, right? So this area is what I am looking at. Okay, this big sort of area. So it's sort of similar to what we did on this side, except it's floated or flipped around on the y-axis side, right? We did something like this for x tending to infinity. X tending to 0 plus also we are going to go this way. So you can easily guess this minus log x will tend to infinity and log x will tend to minus infinity as x tends to 0 plus. But I just want to show you that same area type calculation here. How do you get an easy lower bound? I will look at this area, okay, and then this area, and then this area like that, right? And what is each of these areas? This area is 1 minus x, isn't it? 1 minus x, this area, and then this area is half minus x, okay, 1 by 3 minus x, so on till 1 by floor of 1 by x. See, this 1 by x is there, and floor of 1 by x is the point here, and that one floor of 1 by x minus x. Okay, so this is the thing. I don't want to go into great detail here, just check it out. But basically what happens is this becomes 1 plus half plus so on till 1 by x minus x into floor of 1 by x. This x into floor of 1 by x is sort of like 1, okay, or you can upper bound it or lower bound it. It's easy to bound this. It's between 1 and 2, for instance, and then so it doesn't really matter as x tends to infinity. Why? Because this summation is blowing up to infinity as x tends to 0. Okay, so as x tends to 0, this doesn't matter too much to me, and this one is tending to infinity, okay, as x tends to 0. So that's the crucial point here. But main thing to understand is these two results. As x tends to 0 plus, log x is tending to minus infinity. As x tends to infinity, log x is tending to infinity. At 1, it's 0. Okay, so it has a picture like that. Okay, so I'll show you the picture soon enough, but these are quick proofs to show you what happens to log x at either end. Okay, it blows up on either end. Okay, okay. The crucial property of logarithm is that it is the inverse of the exponential function. Okay, it's not obvious at all from the way I've defined it. Okay, I've defined log x as a function whose derivative is 1 by x, right? That property makes it the inverse of the exponential function. It sounds surprising, but it's very true. Okay, so notice why that works. If I take log of e power x, okay, so if I claim that log is the inverse of e power x, what should happen to log of e power x? What happens to the inverse function? If I have a function f of x, if I do f inverse of f of x, what should I get? I should get x, isn't it? That's the inverse, no? I go from x to f of x. F inverse will take me from f of x to x. So f inverse of f of x should take me back to x, right? So log of e power x, I expect it to become like x if it were a inverse. Okay, but to show that, what I'll do is I'll take its derivative. Okay, so if this is x, what should its derivative be? 1, isn't it? And that magically works out because of the property that e power x is its own derivative and log's derivative is 1 by x. Okay, so you notice that just comes very, very easily. Log of e power x, if I take a derivative, I get 1 by e power x times e power x, right? This is the composition rule of logarithm, no? The composition of rule of logarithm is what is going to help you in establishing this fantastic property. E power x, which we defined as the power series 1 plus x squared by 2, and log x, which we defined by the integral, these two happen to be inverses of each other because of this wonderful property that e power x is its own derivative and log x's derivative is 1 by x. Both of these are special functions and they are inverses of each other. Okay. In fact, you can also go the other way around. I started the definition of logarithm as integral and then came to this. You can start at this point and go back to that. Okay, both ways it's possible. Anywhere, somewhere you have to start. You start logarithm as inverse of exponential and you can show the integral property. You can start logarithm as the integral definition and come to this inverse property. Both are possible. Okay. So now derivative is 1 doesn't mean log of e power x is equal to x, right? Log of e power x is x plus c. Some of you may be thinking that, but this is easily settled if you put x equals 0. Notice the choice of log 1 being 0, that was crucial here. So if you actually put x equals 0, log of 1 will be 0 and then 0 equals 0 plus c and that c becomes 0. Okay, so check this out. So I told you why we choose then the integral, the base integral a as 1, no, integral 1 to x. If you choose something else other than 1 here, the c will not become 0. So you won't get this log to be a perfect inverse of the exponential. So that comes from that choice of 1. Okay, so you have to choose it like that. So you put x equals 0 and log 1 will become 0 and 0 equals 0 plus c and c is 0. Okay, so that's the important thing. So log of e power x is x. Okay, so now here is an interesting and important thing about inverses. You may not have thought about it, or maybe we didn't see it in this class at least. So if I have f inverse of f of x being x, okay, this implies f of f inverse of x equal to x again. So if f inverse is the inverse of f is the inverse of f inverse. These two are true. The range and domain and all matter, you know. For instance, you know, I write log of e power x is x. Okay, e power x is a function that takes the real line to the positive real line, right? So what do I mean by that? E power x can belong to R, but e power x is always greater than or equal to 0. Okay, so e power x takes the real line to the positive real line. Okay. Now log has a very interesting property, right? Log of x will take the positive real line to the real line, right? Because log of x has to be greater than or equal to 0. Yeah, I'm sorry, not greater than or equal to 0, greater than 0, and then that will take, you know, it takes this r plus 2, it can go from minus infinity to infinity, isn't it? Log of x being x close to 0 is minus infinity, x being very positive is infinity, so it takes you all the way through. Log of 1 is also 0. So it takes r plus to r, and then e power x takes r to r plus, well, actually e power x can never be equal to 0 also, right? So r plus is there. Okay, e power x is greater than 0. Let me not say greater than or equal to 0, I'm sorry. Okay, so this is something that we have seen. Okay, so this property is also important to know. So if log of e power x is x, and what will happen to e power log of x, that will become also x. Okay, so both of these are true, and this gives you this this picture of e power x. I just wanted to draw it and show it to you also. This is y equals e power x in the xy plane, and I've drawn this picture. If you take an arbitrary point x naught on the x axis, that goes to y naught on the y axis, that's a point x naught comma y naught. So y naught becomes e power x naught and x naught becomes log of y naught. Okay, so log of e power x naught is x naught itself, right? So x naught you go to e power x naught and then you take log, you come back. You have y naught, you take log, you go here, you take e power, you go back. Okay, so that's the reason why this f of f inverse is the same as f inverse of f. Okay, so f inverse goes in one direction, f will go in the other direction, it will give you the same thing. Okay, so that's what's going on in this picture. So this picture is important to understand. So this picture, which is actually the curve of y equals e power x, also gives you the curve indirectly of y equals log x, right? Because if you just flip the axis roles, you go from y to x, you get log. So you can use this curve to find both e power x as well as log x. Okay, let me show that to you a little bit more precisely. If you plot logarithm and exponential functions, okay, this is the way to do it. You have y equals e power x, that's this red curve here. you flip it or you reflect it about the y equals x line, right, x equals y line, you get the y equals log x curve. So, this is how you find the inverse. This is one more way to find the inverse. Okay. So, you have one plot, you take the x equals y line, you flip it around it, you get the inverse of that. Okay. So, you can check this out, you can see there are a lot of graphical ways to visualize this. If you have an x, right, if you have an x here, you go to e power x, right. So, that same x becomes y here and then you go to log. Okay. So, that is the inverse logic for this. So, there is a interesting logic here, but anyway, so this gives us a very nice way to visualize the y equals log x curve. So, y equals e power x curve and y equals log x curve. Notice the y equals log x curve, this point is 1, okay, at 1 it goes to 0, right, and as x becomes greater than 1, it continuously monotonically increases to infinity. This point is 0, you know, as it tends to 0, you tend to minus infinity, and from minus infinity you are monotonically rising all the way to plus infinity, right. So, this is how the point curve looks. I hope you can appreciate this reflection and all these things. Think about these things for a little while. It's a very nice way to think of the log function. So, this gives you a very nice plot of log. You can plot these things in Desmos and try and understand it a little bit better. Okay. All right. So, so let us stop this lecture at this point, and the remainder of this lecture we will look at applications of logarithm and some problems. Thank you.